We love technology when it works. Yeah, which is not always. All right, so Canvas, things I wanted to bring to your attention. So I'm clicking on the stat hexagon. That takes us to our class website, housed on my personal website. I have added some things this afternoon. So I rearranged this resources section, and here I have linked all the different YouTube playlists that I have. And I have added two things here. These are PDFs you can download. This first one is a multiple page formula sheet for all the formulas we use throughout this entire class. And the second one are the tables, the Z table, the T table, all those tables in the back of your book, if you don't want to haul your book around. I usually keep copies of these two handy when I'm working homework keys and answer keys and stuff like that, because it's a lot easier than flipping through the book. So I want to show you the formula sheet first because we're already well on our way. So I just did it on another. This is the PDF. Now I started making this first page, arranging this when I used to teach Stat 1040 here at the university, undergrad Intro to Stats, and I've kind of beefed it up and rearranged it and added more stuff. I used to have it blank and then have my students fill it in as we learn these things throughout the semester. So if you look at the top and see the title, it's the filled in version. And this was made in Word, and it just about killed the last brain cell left in my brain. But I haven't attempted to redo this with LaTeX equations. So this page is all about comparing group means, whether they're one group, two groups, matched pairs, pre-post. We're comparing group means. And so here it says X is a measurement in the sample. Mu is the population's mean that we don't know, but we're hypothesizing about, and we want to make an inferential statement about. So it's arranged. So up here at the top, these are the formulas that involve only a single sample. So far we've done the z-test for one sample and the t-test for one sample. And you notice these formulas are almost identical, but in the z-test formula we use sigma. So you use that if you know the population standard deviation, or when the sample is very large. So if you have a very large sample, you can do a z-test. Or if you know the population standard deviation. Most of the time, that's not so rare. That's pretty rare in social science. Usually we either have a smaller sample or we're using the sample standard deviation. In that case, when we're using little s instead of sigma, the sample standard deviation, that's a t-test instead of a z-test. And we have to have the associated degrees of freedom. And the formula for degrees of freedom is sample size minus 1. Now over here I put the Cohen's d formula, but I just noticed this today. What is it dividing by? Standard error, and it's supposed to be standard deviation, so I need to fix this. Nobody's picked that up for years, so I need to fix that. And so here are the hypotheses, and we've learned this. How do you calculate standard error? Standard deviation divided by square root of n. If we're doing z, it's sigma. If t, it's s. And so this is if we're doing one sample mean. So this is the summary of the last two chapters, 5 and 6? We're going to skip this middle part that's grayed out. This is for matched pairs. And then down here is if you have two independent samples. So this is starting chapter 7 that we're going to start into today in the lecture. But you'll notice we can do a Z or we can do a T. But the arrangement of the page is about the same. We have what situation we're in, the estimate that we're going to make, the critical value, CV is critical value, how we estimate standard error. What do you notice about the formula as we move along in the sheet? It gets a little more complex, right? And then here's hypotheses, the test statistic, and then some notes over here. So this is the first page of the formula sheet. This is, these are all T and Z tests. So that's going to take us through the first half of the chapter, or the course. What happens in the second half of the course? What do we start covering? ANOVAs. But here on the back, coming up is a chapter on effect size and power analysis. So here's our formulas we will get to for effect size. You don't really need to memorize the formulas. You will find that you will start memorizing them because of using them, but test-wise, you'll be given these. And you notice in the homework, you're given little formulas. It's not necessary to memorize them. We will get to post-hoc test after we start ANOVA. And then there's all these ANOVA things that come after it. So it's 1, 2, 3, 4, 5 pieces of paper. And you can print it front, back, whatever you want. So those are all the formulas. Now the book is pretty good. I'm trying to not overwhelm you with math, but it still has a lot of formulas. A lot more formulas in the chapters than you really need to know. They're trying to show you where the formulas come from, and might be too much sometimes. Okay, so then the other, what do we say? This other one is the tables. So it just has that Z table, the T table, and on and on. So that's where you can find them if you just want to print those pages. And here are the slides. So last time we had to go to Tyson's page to get the Chapter 6 slides, and I have updated them here. And Chapter 7, which we're going to get to after we kind of review what we didn't get to before on Chapter 6, including some homework questions, we'll start on Chapter 7. This is a PowerPoint. This one hasn't been updated. None of the other chapters have been updated into R. We'll see how many I can get done. My goal is to get them all done this semester. So we're getting some more there. Okay. Before we move on, there were some questions that were in Chapter 5, which I wish, darn vacation, we should have addressed in class before that was due. So I'm probably going to, when I start grading tonight, adjust scores because we didn't go over these. But I wanted to talk about, in Chapter 5, questions 52 through 56. They were on the discussion boards, those 50s. Do you guys like that it shows that there's like 60 questions? I mean, a lot of them are just like one number. Would you rather that they were like a box that had like 4 things to fill in the blank? Or do you like to see that you're making big progress? I look at that, I'm like, 54, that's a huge assignment. It is overwhelming.
Just so you didn't have to scroll back and forth for formulas and stuff. So
it was, yeah, I'm going to be, be in a table, like fill, the z-score is blank, the p-value is blank, is one thing instead of having, that's, I was like, yeah, that's a lot of scrolling, it goes forever. I'll see about reformatting. Or is it for, which one is it for? Yeah, okay. So the ones, this is how it used to be on the, when we did it on paper. So I like this format better. If anyone likes this, I can upload these if you want to look at the paper ones, if you are a fan of writing or seeing it all on one page. But these were the questions, and these were, it's in Chapter 5, Section B, and in the textbook, they're number 11, 12, and 13. But let's see. What does alpha stand for? It was had part A, B, C, D that were true, false. Alpha. Let's see. I'm going to read these one at a time and figure out if it's true or false. Alpha stands for the proportion of experiments that will obtain statistical significance. Does alpha tell you how many of your experiments will be statistically significant? No. Okay, I'm not doing these I'm scrambling the order. The proportion of experiments for which the null hypothesis is true. No. Alpha, the proportion of statistically significant results for which the null hypothesis is true. It is not that one. That is false. Alpha is, this is the only true one, the proportion of experiments for which the null hypothesis is true that will obtain statistical significance. So p-value and alpha are based on the fundamental assumption that the null hypothesis is true. So it's kind of screwy in that you assume the null hypothesis is true to run an inference test, even though in your mind, you're probably thinking it's not. So that's what makes these alpha and p-value and inference be a little bit counterintuitive. I think that is like 48 to 51-ish on the homework assignment. Let me see if I can pull it up so we can look at it together. The only way to get the problem numbers is for me to go into student view. It doesn't show me the numbers 1 through 379, whatever the poor assignment goes to. Okay.
Oh, okay. I needed to see the choices to know
What you'd put.
Well, no, I needed to see the choices to know what the difference was.
Yeah. The wording is very subtle. Okay, so resume quiz, yes. So yeah. Yeah, all these little 1.1s, yeah.
Oh no, you're right. Yeah. Hey. Lovely.
Yeah, it's not a number. Right here, this one. That was the one. What does alpha stand for? Okay, so these are pretty tricky. In the textbook, it's page 163, 164, 167, 168. There's a figure at the bottom of page 166. Let's see if I can pull up the textbook so we can look at it. What does this figure look like? Figure at the bottom of page, we can go to 166. Figure 5.9, so here's this figure, right here. Total number of statistically significant results. So we have null experiments, alpha, ineffective experiments, 1 minus alpha is power, total number of significant results. I don't know. Now, there's the figure anyway. So let's go back to here. So this is the question. In the last few years, an organization has conducted 200 clinical trials to test the effectiveness of an anxiety drug. Supposing, however, that all of those drugs that they tested were from the same fraudulent supplier. So we are saying that all of those drugs are ineffective. They're all pretty much sugar pills. They do nothing. None of those drugs work. None. Which was later revealed to have sent an inert substance, distilled water, sugar pill, something that does nothing instead of the real drug. If alpha equals 0.05 was used for all of the tests, because, that's the golden rule that everyone loves, how many of these 200 experiments would you expect to yield a significant result? 10? How many? 10? Why 10? 1 out of 5? 1 out of 20. Yeah. So 5% is alpha is essentially the false positive rate. How many of these should give significant results? None should. They're all fake drugs. But we would expect about a 5% false positive. So we would expect about 5%. 5% of 200, 1 out of 20, if we have 200, is 10. So we would expect about 10 of those experiments probably would have said something was going on. How many type 1 errors would you expect? Yeah. It would be the same. Why would it be the same? Because none of them should have been. So all the significants were false significant. So all of those 10 were false positive. So there would have been 10 type 1 errors. Now here comes another tricky one. How many type 2 errors would you expect? Yeah. What's a type 2? It's a false negative, where you would say nothing's going on, but it really is. How many of those drugs really work? None of them. So can you make a false negative? No. So 0. That one's tricky, but this next one is even trickier. I will grade accordingly because I always do this in class before it's due. Sorry. Since she arrived at the university, Dr. Pine has been very productive and successful. Got lots of publications. She's already performed 20 experiments, and all of them, every single one of them, has reached a 0.05 level of statistical significance. What's your best guess for the number of type 1 errors she's made? 1? No idea? You don't know.
I don't think there's a way to figure it out.
There is no way to know. What's the least she could have made? 0. What's the most? 20. If she did 20 experiments, you could have had all of them be truly positive or 20 of them to be false. All of them she got positive, said were statistically significant. Those are positive results, positive. So we have no way. Remember, alpha 0.05, the false positive, is if the null hypothesis is true. What if she's testing things like there are more accidents for people over age 14 than under age 14? Drivers age 14 or over versus drivers under age 14. What if she tests the experiment that, or the hypothesis that the average college age of college students at Utah State is greater than 10? Can you pick hypotheses that are pretty much guaranteed to be true? You can. So false positive and false negative, type 1 and type 2 errors, depend on the null hypothesis being true, and we have no way of knowing the truth in those experiments. Maybe she picked easy to prove things. We don't know. And the last one. What is the number of type 2 errors that she made? 0. Why 0?
Because she had no negative.
She had no negative results, so she can't have any false negatives. Yeah. If those make your brain hurt, then you're thinking hard, and that's what I want. Because it's counterintuitive to think of p-values. People think a p-value tells you the chance that the null hypothesis is true. It's not the chance the null hypothesis is true. It's the chance of observing that extreme data if the null hypothesis is true. You're always standing on the assumption, assuming that the null hypothesis is true. And that's awkward because as a researcher, we don't want to do that. We want to know what's the chance we're wrong. And we can't say that. It is awkward. Okay. Well, we're doing homework questions. Let's switch over to homework 6. Questions 8, 9, 10, and 11. This one's not due till tonight. Yeah.
That was my question, and I figured it out. So.
Oh, you figured it out? I still want to go over it because it's a good one to go over. Yeah.
Before we get to that, can we look at question 6?
On homework chapter 6. Okay, let me open up chapter 6.
I flagged it, and I think I was just, when I looked at it, I just wanted to be sure I picked the right number.
Okay. So, let's see. Let's open this up. This numbering system that I don't understand. Okay, so number 6. Let's see. Question 6. So here it is. So it's the sample standard deviation.
So that's the one that's given up on the...
Now, you have to look closely on here. This is S of X, not S of X bar. Okay. Let me see. Which one of this is? This is chapter 6, section A, number 2, 6.2a. Yeah, this is the one I wanted to go over. Okay, so we got some formulas. Background. Yeah. So survey is of 144 college students. So that's our What letter would we use to be 144? N. Reveals a mean beer consumption of 8.4. 8.4 is what symbol? X bar. With a standard deviation of 5.6. 5.6 is S of X. That is S of X.
I thought that's what it was, but
S with a little x. No bar.
So S
and is that what goes in the
X
top
is the
before
same
goes
thing
as one?
as SS?
Yes. Yes. Okay, so this is why this is good. I want to go over this. Yeah.
That's what got me confused because
Okay. So this is N is 144. X bar is 8.4. This S, little s, is the same thing as little s with a plain x. But if we want to do S of X bar, what do we have to do? 5.6 divided by square root of 144. Which is, what does that equal? 4, 6, 6, 7. How many decimal places? I'm going to go in there and I'm going to put how many decimal places. I got to work ahead of you enough that I start on the next one before you get there. That's the trick. Because once somebody opens the assignment, I can't change it for you. That's the way it works. Because it says, somebody's already started taking this, you don't want to change it. So the next one I'll do that. Yeah. So in the formula, this little S, an S with nothing on it is an S with a plain X. But an S with an X bar, and these are teeny. I'm going to see if I can make them a little bigger, is the standard deviation for the sample average. This is the standard error. So this one is the standard deviation. This one is the standard error. And when we make the z-score, which one goes on the bottom? The standard error, not the standard deviation. That plain S means S sub X could easily have been missed. The book, I think, says it at some point, but it's very buried at this point. Yeah, so S by itself is S with the little x. Same thing. But S with the X with the bar has to be shown. So the first thing is, so now we need to do the z-score and the p-value. So when we do the z-score, did someone get a z-score? How do we do the z-score? Okay. Okay, so there's another number in here. It's not a number, like a digit. What's the number in here that's important? The national average of 7. So the null hypothesis is that the average of the whole population equals 7. So this 7 is mu of the null hypothesis, or what goes right there in our formula. So if we're going to do the z-score, is going to be x bar minus the hypothesized average over the standard error. Yeah, and that comes out to be 2.9997. So it's basically, it's going to round to 3.0.
I think mine went to 3 because I put it out to 4.
Mm-hmm.
And then it rounded it up.
Yeah, it's 3, or wait, not 3, it's 2.9997.
Yeah, something
5. So if you round it to 4 or fewer decimal places, it equals 3. So the z-score is 3. How do we find the p-value? We got to go to that chart, which that's the formulas. Luckily, I gave you that link with the tables. Okay. So this first column is Z. Here's the middle, and here's the beyond columns. So here is Z is 3. So there's the middle slice, and here is the beyond area. If 0.0013 is the beyond area, it's the p-value 0.0013. It depends. That's the right answer. What kind of p-value were we doing? A one-tail or a two-tail? Does it say?
It doesn't say. That's why it's.
It doesn't say, so we have to do a two-tail. So it's saying if our z-score is 3, this tail is 0.00113. That would be our one-tail p-value. But since it didn't say one-tail, we have to double it to get the two-tail because it didn't say to do one-tail. So if we double it, then this tail would also be 0.0013. So your p-value would be 0.0013 doubled times 2. You haven't, it's not due yet, so you can go fix it. Okay. It's not specified, it's a two-tail. If it doesn't say, it's a two-tail. Yeah. And you can go on the discussion board and say, hey, on this question I got this. Did anyone get the same thing? And you can check with each other, even if you can't find a time when you can meet together to go over this. And I will try to chime in. Okay, so that was what? Problem, that was that 8 and 9. So 8 says, what's the z-score? The z-score is 3. 9 says, what's the p-value? 0.0026. Yep, so 10 and 11 are the next ones. See, we know this. I know this. This is going to be questions. Okay, so is this the right? Am I in the right spot?
Yeah, we just had to fill in the stuff.
Okay, so mu n x bar s x. So there's the z is 3 is number 8, and the p-value 0.0026 is 9. So now here's the next problem. So we're still working on the same stuff, but if the national average were 4, what was it before? 7, what would be the z-score and the p-value? So what would change? So now we're saying the null hypothesis is mu equals 4. So what's going to change about the z-score? What was the sample average? 8.4. But now we're, instead of subtracting 7, we're subtracting 4. That's what we changed. Do we change the standard error? Because where does the standard error come from? Sample standard deviation divided by sample square root of sample size. Did any of that change? No. So that's the same, what was it, 0.4667. So you get something, a different z-score. Before our z-score was 3.000. Now what do we get?
9.428.
Or 9.43. How, either of those is fine. Yeah. That's our z-score now that we've changed our null hypothesis instead of 7 down to 4. That's not a fun look. Why is this?
I had a number that was slightly higher. I'm not sure how I got it.
I don't know either. Okay. So what do we need to do now? We found our z-score. That's for 10. 10 says, what's the z statistic, the z-score? 9.43. The next one, question 11, says, what's the p-value? How do we find the p-value?
Well, it's on the table, but it only goes to 4. So
Ah!
economically high.
We've got to go to that table, but the table only goes so far. Why does the table not go any further? It stops when z is 4. Why did it stop at 4? We need to go to 9 point something. Because look, what's our beyond area? Teeny tiny. So if going out to 4 standard deviation, it's that small. What's going to happen if we go out to 9? How much is going to be in that tail beyond there? Like pretty much nothing. But we got to double it, so now we have double almost nothing. So what do you type in the box for the p-value? This has me wondering what Jeremy put. Oh, you have an option. Yeah. Well, because, yeah. Is that, which one is it? Significant. Listen, how would you write it on a publication if you're typing your report? Less than 0.05? No, 0.001. The last number has to be a 1. You can't end with all zeros. And if you're doing your p-values to 3 decimal places, be consistent, 0.001. If you're doing p-values to 4 decimal places, be consistent, 0.0001. Usually in APA we do 3 decimal places, but there are times when we'll go out to 4 consistently. Just be consistent, less than, point, all zeros, and then a 1. I was wondering how that would have been typed in there. Jeremy did a good job. Okay, does that help with the homework? Yeah. Okay. Yes. Before we do the one on the homework, can we do the slides? That might help clarify. So here's our slideshow. So we were doing these last time. So here we go. Confidence interval. So a confidence interval is helps you tell like how sure or what's the range, what's our margin of error. You know, we're election time, you know, when you see the election results, this candidate is ahead by 3%. In the bottom it says plus or minus 3 percentage points. Yeah. So that plus or minus is the margin of error in a confidence interval. So time we take a sample, our sample average or sample standard deviation or sample whatever, median, the sample value is our best guess at the population's value. But is it going to be perfect? Never. If we take a different sample, we'll get a slightly different answer. So the confidence interval gives us a range, a margin of error, to let us know how accurate and precise we are with our sample. Now, the bigger the sample, the more tight our margin of error is going to be around our best guess. Now, the best guess is called the point estimate because it's just one number, one point estimate. So sometimes you'll hear about point estimates versus confidence interval, and that's this idea. Your sample average is your point estimate for your population average, and your confidence interval includes a margin of error on either side. So, in general, to have a narrower confidence interval, we usually need a larger sample. So to get a tighter, smaller range, we need a bigger sample. If we have a smaller sample, it's going to be a bigger range. The other thing is that we can change the percentage. Most of the time, confidence intervals are done 95%. We want to be 95% sure we have the truth in our confidence interval. Sometimes we'll do a 90% confidence interval, sometimes a 99%, sometimes an 80%. You could do a 37.5% confidence interval. Don't know why, but you could choose any number there. So most of the time we do a 95% confidence interval. Now if you're doing a 95% confidence interval with a z-score, what do we see? A z-score bell curve to get 95% in the middle. How far do we go out? How many standard deviations? About 2, we go out 1.96. So if we're doing a z-score around the average, x bar, to be 95% sure, our margin of error is going to be 1.96 times, what's this thing right there? Sigma divided by square root of n. That's the standard error. So we do 1.96 times the standard error. And we add or subtract that to get the upper and the lower edges of our confidence interval. If we want to be more sure, 99%, we've got to go out further. To get 99%, we have to go more than 2 standard deviations out. And this is what the table value will give you. So if you're doing Z confidence intervals for 95, 1.96, for 99, 2.58. Those numbers come from the calculus that you don't want to care about. Okay. So let's do this example, and then we can see if you can match that to the homework. So this is the same numbers that were on this one here. So when we did this before, I'm going to write this on the board quick just so that, because I don't want to keep memorizing it. I printed it out and left it on the printer. So we have, how many numbers do we have? 10. What's the average of that list of numbers? 7.6. What's the standard deviation of that list of numbers? Okay, my philosophy is while you're doing calculations, keep 4 decimal places. When you're done, 2 or 3 is enough. But if you chop it down to 2 while you're working, you get round off error snowballing. So 7, 9. Okay. So there's our information. Oh, and what did it say? In the past, what's the average? A 5. Our hypothesized value is 5. Okay. So here's the doctor, the physician, that thinks that his patients in the past have visited 5 times a year. I don't know if these are like diabetics or certain kind of, because do you guys go to the doctor 5 times a year? I don't. But anyway, so here's our random selection. So now we want to construct a 95% confidence interval. What's our best guess at the true average? 7.6 is our point estimate. That's our best guess. But how do we make a confidence interval around it? 1.96 times the standard error. So we said n is 10, x bar is 7.6, standard deviation 4.24979. So this is our best guess. And now to do our margin of error, we're going to do 1.96 times the standard error, which is going to be S divided by square root of n. So 1.96 times 4.2479 divided by square root of 10. And that's going to give us our margin of error. Now, who's got a calculator handy? If you have an iPhone, did you know this on your calculator? If you turn it sideways, you'll get the square root key with a bunch of other ones. You are allowed to use your phone on the test, but you can't a calculator that has a square root button. 2.6? 328. Anyone second that? Yeah? Square root of 10 is 3.1623. Yeah? Okay. So to do our confidence interval, we take our best guess, 7.6, and we plus or minus. Now, that's after you times by 1.96, right? The 2? Yeah, okay. So we plus or minus 2.633. So your confidence interval has a lower number and a comma and a higher number. Are we going to add or are we going to subtract to get the lower number? Subtract. Usually, naturally, we would add first. That's going to be the upper one. The minimum, the smaller number should come first. The maximum or the bigger number should come second. So just make sure when you write them down, I think on the homework it has different entry box and it says lower and upper. Make sure the lower one is when you subtract to get the smaller number. or else it might get marked wrong, and we don't want to have that happen. So 7.6 minus the 2.633, that gives us the lower number. And then when we add them, we get the higher number. How many times do the people in the sample visit the doctor in a year? In the sample, these people visit the doctor 7.6 times. That's more than 5. But is it a little bit more than 5 or is it a lot bigger than 5? Well, we can use a p-value or we can use the confidence interval. Are we sure this is exactly true? No. But we're 95% sure that the true average is somewhere between almost 5 and 10.25. Is that bigger than hypothesized value of 5? No. So can we say for sure that they visit the doctor more than 5 times? No, because our hypothesized value, 5, falls inside this range of possibility. We're 95% sure it's here, and 5 is included in there. So we can't exclude 5. So this fails to reject the null hypothesis. So even though 7.6 is bigger than 5, it could have come out to be as low as 4.9 because we only sampled 10. And that's got, and with this amount of spread. So just because 7.6 is bigger than 5, that's not by itself enough evidence. We have to also take into consideration sample size and spread in the standard error, assuming it's normally distributed to make the range. Okay. Do we want to look at the one on the homework now?
I think I know how to do it.
Yeah.
There's just, so the one on the homework, when I was looking at it, has number of friends, and I, like, for an average, I got like 12.3 or something and rounded it up to 13.
Okay, so which one is this?
63.
Oh my gosh, that sounds awful.
But I was just wondering if I should have rounded it that far up. 'Cause I
Yeah.
think you said if we had people, we should always round up.
Okay, for the sample size, we should round up. Just for the sample size. No. So this is the one, right? Not far enough? Oh my gosh, how long is this stinking?
I got 12 right.
This one. Okay. So, what did you get for the average, the sample average, X bar?
I got, well, I put 13, but I got 12.33, but that was
12.33 and
11.53, so I might have done something. So what'd you drop?
12.33, 12. Oh, we got several 12.33s. Yeah. The button pushing. Yeah.
That's 64, 65 marked.
Yeah. So if you're doing, so here's the formula for confidence interval. So it's 12.33. Now, look at this confidence interval. It doesn't have the Z, 1.96. What does it have? T. Why is it using a T instead of a Z? Because we don't know the population standard deviation. We're using the sample S instead, and it's a small sample. This is more common that we have a smaller sample and we're using S instead of sigma. So how do we figure out what T critical value should be? It's not 1.96. It's going to be a little different. We got to go to the T table. Now to use the T table, we need to know how many tails, what alpha, and how many degrees of freedom. So how many tails? A confidence interval always has 2 tails, always. Because it's always, the confidence interval is always the middle, so that means 2 tails. How much is going to be in the tails? Well, what percentage confidence interval are we trying to do? 90. If we're doing a 90% confidence interval, what's the alpha? 0.10, not 0.05. An alpha 0.05 partners with a 95% confidence interval. That's why 95% confidence intervals are used the most, because they partner with a alpha of 0.05. That's kind of a standard fall to. So when we go to our, now how big was our sample? What was our sample size? 13? 15. Okay. So we're going to go to our table, to the T table. So we're all, for a confidence interval, you always do the two-tail. If you're doing a 95% confidence interval, you use alpha of 0.05. We're doing a 90% confidence interval, so we'll say alpha is 0.1. So that's this column. And our sample size was 15, so our degrees of freedom is 14. So what critical T value do we use? Which critical value? 1.76 instead of the 1.96. So if we're doing a 90% T confidence interval with sample size of 15, then we do the two tails, alpha equals 0.10, degrees of freedom equal 14, and that on the table tells us our T critical value needs to be 1.761. Okay. The way we use this T table is different than the Z table. It's set up differently. Need some practice. That's why there's so many homework questions. Okay, so if we go back to the homework question. So what did we So we decided that there were, I keep wanting to write on the board. We decided there's n equals 15, so degrees of freedom are 14. The average was, what did you say, 12.333. Anyone find the standard deviation?
I think it's 5.3807.
Look what I'll do. I'll take this, and I'm going to go into R, because I'm lazy. Okay, you can type right in the console here. I'm going to say X is equal to this list of numbers. So if I type X, it'll give me that list of numbers. I can say, what's the mean of X? 12.333. I can say, what's the length of X? 15. So there are 15. I can say, what's the standard deviation of X? Do you want to do it by hand? On the test, I will not ask you to do the standard deviation of a list of 15 numbers by hand, because rude. I mean, who wants to do that? I mean, ugh. 15. This is why on the slide I showed you how to do this, so that you don't have to, kill yourself off trying to do. Standard deviation by hand is just, I am not a fast arithmeticer. Okay. Yeah. Work smarter, not harder. Okay. So to do the confidence interval, what's the formula for the confidence interval? You take your best guess. What's our best guess? Our average, X bar, and we plus or minus our margin of error. How do we make our margin of error? T critical value times standard error. Now we have all our pieces. What was X bar? The 12.333. What was the T value we looked up? 1.761. Oh, here we go. We looked up S. divide by the square root of 15. Ooh, we should have done that in R while we were there, right? Shall we? I'm going to have to erase this. I can't save it while I switch programs. Okay, so let's go. The SD of x divided by the square root of 15. Don't we like R? R is just a big fancy calculator. And see, I only have to type this set of numbers once, and I actually copied and pasted it from Canvas, so I don't have any possibility of mistyping it, and I don't have to worry about retyping it. Just X means that whole list of numbers. Take out the ability to make a typing error. So our confidence interval would be our best guess, 12.3333, plus or minus 1.761, that critical value, times standard error of. So we can actually type that in here. Oh, watch. Mean of x minus 1.761 times SD of x divided by square root of 15. Now, have you guys figured out this trick in R? What if I want to type that all again? Up arrow. If you hit the up arrow, it redoes the last line you typed, and you can keep going up, and you can go back down. So what's the only thing I need to change on this line now? Change the minus to the plus. Work smarter, not harder. Why do we keep getting further and further behind? No, this is good. The idea of a confidence interval, the point estimate, a p-value, and a confidence interval, those are themes that are going to continue every day of this class and every statistical method you ever do. So understanding them is crucial. Yeah. On 61, on that homework. Okay. Yeah, how does knowing the confidence interval make answering the p-value significance level question easier? So this applies to which question? This is the, scroll. This one. So there's empty parentheses. The mu symbol is supposed to be in there. Or, wait, it says a sample mean, so that should be x bar. I just noticed it's empty. I don't know why. So they give us a bunch of information, and they ask us to find the confidence interval. And then, so here's the pieces. So we make the confidence interval. It wants us to know if they were statistically significant or not. Okay, notice this. So this one's talking about the 95% confidence interval. This one says the alpha 0.05. They're linked ideas. So, does anyone have what the confidence interval ended up being?
2.317 and 2.883.
This is the confidence interval. This is the 95% confidence interval. Okay. This one asked us, they want to know is the European study had already estimated the population mean mu was 3. They want to know, is it different? Here's the magic number is 3. That's the hypothesized value. Is it inside the interval? No. So if 3 is not inside the interval, then we can say it's significantly different than 3.
So we can compare with mean and
Yeah, we see is the hypothesized value inside the confidence interval. And if it's not, then we know the p-value is going to be smaller than 0.05. So that's like the way that they link. So if our hypothesized value is not in the 95% confidence interval, there's the if, then the p-value will be what? Significant, so less than 0.05. If our hypothesized value is not in that interval, then we know the p-value will be smaller than 0.05. And the reverse is true. So what if the hypothesized value is in the confidence interval? Then it's going to be not significant. The p-value will be bigger than 0.05. So one batch of statisticians were working on the confidence interval idea. At the same time, another group of statisticians were working on the p-value idea, which the math is roughly the same. And this was back in the day when journals were like letters, and they wrote scathing articles against each other, back and forth, that their way was better than the other way. And the conclusion is much the same. They're not the same idea, exactly, but your takeaway, whether you have evidence against the null hypothesis or you fail to reject the null hypothesis, is the same conclusion. The thing with the confidence interval, you just say it's going to be bigger than or less than 0.05. It either is or is not inside the interval. The p-value, when you get it to 3 decimal place, gives you more strength for the evidence. Because there's a difference between a p-value of 0.05 and a p-value of 0.00000001. Like, how far outside the interval is it? Yeah. The one right after it? Okay. So this is a rearrangement of the formula that we were doing before, the Z formula. This W is the width of the confidence interval, how wide it is, which is 4 times this, well, almost 4 times the standard error, because it's like critical value, which is almost 2 this way, and critical value. Anyway. You can put your numbers in here to find out the sample size. What's little s? Standard deviation of the sample, the values in the sample. What's W here? Width. So they want the width to be a half an hour. So what number do we put in for W? 0.5. So S is a number that we got before. So you do 4 times S, divide by W, and then square it. Now on this one's asking about sample size. So we round up no matter what. So 6B, number 5. Yeah. What'd you guys get? 208. Yeah.
How do we decide the critical T if our degrees of freedom isn't exactly on the table?
Ah, this is a great question. Yes, thinking question. What do we do here with the T or Z? This was the Z table. What happened if our Z was off the table? We just kind of extended it and we knew it was tiny here, right? So the same thing can happen in the T table, in all of these tables really. So notice the degrees of freedom over here. So we're going 1, 2, 3, 4, 5. Well, I'm going to scroll down to the bottom. Check out the degrees of freedom at the bottom of the table. What happens? What happens after 30? 40, 60, 120, and what's the last line? Infinity. Remember the shape of the T. What did the T curve look like? The normal curve, but squished. As the degrees and the less the degrees of freedom are, so the more degrees of freedom, the closer to the normal curve. So when your sample gets big, it becomes almost the same as the Z table. So what happens to these numbers? They stop changing as much. So what happens if your sample size is 36? Which line should you use?
Use
Use R. Yes, you use a computer. For the homework, round to the closest one. So if you need 34, use 30. If you need 50, go with 40 or 60. The answer will be only off by a tiny decimal place, and it will still be okay for the assignment. Okay? What if your sample size is 200? Use infinity. And this infinity line are the exact numbers you get off the z table. Because as your sample size becomes bigger, the t curve becomes almost exactly the same as the z table. And going out to 3 decimal places, once you get a big sample, like over 100, 120-ish, the decimals are so close that it doesn't matter really. That's a great question. Okay. So write up. When you do a statistical test, you are going to have to write about it. And this is how we do. Now, we've already talked about if you're doing means and standard deviation, you can actually write them in words, or you can use parentheses. Where can we use the capital M? Only in parentheses. What if we want to write about the mean and it's not in parentheses? We actually have to say M-E-A-N. We have to spell it out. Z always would come before P. Z and P are never in parentheses. Z and T just fall in the sentence, and it's so awkward, but it's the way we do it. So it says the hourly fee for our sample of current psychotherapists is significantly greater than the 1960 hourly rate. Write the sentence as if you were having no numbers in it, and then you just jam the numbers in when you talk about them. So as soon as you say significantly greater, that's where you got to prove that it's greater, and you prove it with a Z and a P. Now, typically, the Z or the T, we typically use 2 decimal places. This is only showing 1. I realize that. The p-value, we typically use 3 decimal places. So if it's tiny, we say p is less than 0.001. Do I need a 0 in front of that decimal? No. Would I need a 0 in front of this decimal? Yes. So that's how we do Z. With T, we have this extra piece of information. What's the extra piece of information for T? Degrees of freedom. The degrees of freedom go in parentheses right after the T, but before what it is equal to. Now, this t-test happened to have a the z-test on this first one, example is statistically significant. This t-test just happens to not be statistically significant. So we might say, although the mean hourly fee for our sample of current psychotherapists was higher, that average is 72 is higher than 63, this difference only approached, or you could say failed to reach, statistical significance. And then we throw our stats in there. We always have comma. If our stats are in the middle of the sentence, you put commas before and after, and always a comma between Z and P. If it's at the end of the sentence, we have a comma, T stuff, comma, P, and then a decimal. I say there should be 3 decimals after the P value, 2 after Z or T. Is that always followed? No. But it should have this 4.00, and this P value should be 0.06, and then one more number. These were taken out of a textbook, so they're, textbooks aren't always perfect. Okay. Any questions with the R part? How was doing this in R? It's fairly easy in R. And there's no, which line of the table do I use, right? It just spits it out. The thing with the one sample t-test, though, is you have to pull out that variable, say what mu is. By default, what confidence level is it going to do? 95. So if you want to do a different one, you say conf level equals and it's 0.99, not just, if you put 99 without the decimal, you will get an error. Okay, so how would we write that one in a sentence? Just the numbers, not the words, but how would we write this set of results? We would put the T, and then parentheses, 2 for parentheses, equals, and we usually put a space on either side of our equal signs. Equals 2.077, or if we're going to do 2 decimal places, 8, and then comma, P equals, do I put the 0 in front of the decimal? Nope. 0, 4, 9. Now, it is also frequently done that you'd put the confidence interval in there. And you do CI space, let me make it so more obvious, CI without a space, 9, then here's a space, and then another space, and then square bracket, and here's, oh, but this one's a 99% confidence interval, 1, 6, 0, and we usually go one less decimal place. Like that. So, in this one, are the results statistically significant? Barely, right? Barely. And our confidence interval, do you know what the hypothesized value here is? At 99, yeah. This, well, what alpha are you going to use? This is, okay. So our hypothesized value is 165. Are the results significant? At the alpha equals 0.05 levels, are they significant? Yes, because our p-value is less than the 0.05. What about the significance level of 0.01? No, because our p-value is not smaller than 0.01. This confidence interval partners which of these results? 0.01. So it's just barely less, our p-value is barely less than 0.05, but it's not less than 0.01. Now, in this one, for illustrative purposes, to practice, you were asked to do a 99% confidence interval. Usually in a publication, we pick one or the other, and almost always, which alpha do we use? 0.05. So usually in your methods section, you write a sentence that's like, a significance level of 0.05 was used throughout unless otherwise stated. Because this result is significant at the 0.05 level, but it's not at the 0.01. By doing the exact p-value, we can see that, and including this 99% confidence interval helps clarify that the average 178 is bigger than 165, but are we sure that the population as a whole is bigger than 165 in the average? We're kind of on the fence there. It's statistically significant, but barely. Yeah?
So the last question on the R, it asks us to find the 95% confidence interval with R.
Uh-huh.
But then the questions on the homework say what are the lower and upper bounds of the 99%?
Oh, it says 99?
So I didn't know which one.
Well, that's a good, that's,
The answers are 95 because I put in 95 and I got them correct. Yeah.
oh, that's good.
Okay.
So,
Did it R and then switched it back? I can't remember.
Yeah. So in the problem it says
You do
95
what the
and
problem
the answer it says
the answer box.
That's the 82 and 83. That's the one that I have.
It's also wrong though right there in that table. If
Uh-huh.
on the drop down list it says T of 99
Okay.
instead of
Let me fix that.
that would be never mind. That's wrong though. Because that would be the
Okay.
Or 0 to 80.
Will you send me an email or a message about that so I can fix it?
Yeah, I'll look
'Cause-
at it again, I can't remember.
Can we see it?
Can we see it? Okay.
I'm so lost, I don't know.
Yeah. Which one are we talking about?
Question 82 and 83.
Okay.
R is going to give me the answer, and I just put them in because I did the instructions in R, and then I
Mhm.
put my answer questions, and so I didn't really read. I didn't really read what was in Canvas because I was like, if I do the R code right.
So see the message up here. It says students are already taking this. They will be judged on the version it was when they started. Okay, so it's way down here at the end, right? Right here it says 95. Is it this one?
Yep, but then if you go down a couple questions, it says what's the lower bound and upper bound?
Up, you missed it.
Sorry.
PT.
Question 2 and 3. It says 99%. No,
This one?
go down.
Yeah, it's the
Like
lowest.
2 questions.
You're right there.
Oh, right here.
It just says 99, but the answer, I put in the 95% and it was right.
Okay.
What did you put in?
I have no idea. I don't know which one.
72.14.
Probably.
That's what I ended up with.
Whatever R told me.
Yeah.
If in 2 places it said 95 and 1 it said 99,
Yeah.
yeah. But still, if you ever are like confused by that, send me an email or
I think I just checked in the textbook. And
yeah. Yeah, you can also check in the textbook if you're like these 2 places say something different because the textbook, all these questions are coming out of the textbook. So this is chapter 6, section C, problem number 3. Yeah, and R should be right.
R, I didn't put 99. I think I.
Uh-huh. And then there was a,
I think I had 99 in because I pasted it from the.
did you say there was a drop down that was wrong?
The one in the table.
This
I
one?
don't remember. If in the responses for the 95% confidence interval,
Uh-huh.
I think it might have said the 99% in the drop-down list with the answers. It said something about 99. Oh, you can't. Can you see the options for the answers? There was something about 99% somewhere that was weird, but the answers were right.
Okay. Let me see. So I'm going to save these. Now, I fixed them, but I don't think it'll look fixed in yours because you've already started it.
Okay, I was just.
But go 95, yeah. Yeah, ask me in the future. Okay. I feel good with where we've come to with chapter 6, but we obviously have not covered chapter 7 yet. So I will adjust the deadlines for the assignment accordingly, and we'll pick it up with chapter 7 next time we meet, which is Monday. So next week we have Monday and Wednesday, but the week after that, on the 17th, is President's Day, and we don't meet on that day. It's on the calendar. Okay? All right. We feel better about chapter 6 now? Confidence intervals and using the T-table and its weirdness. Okay. Chapter 7 is about doing 2 sample tests, which is more realistic. You're almost always going to have 2 groups, a treatment and a control. We're not going to do it yet, but a pre and a post test. That's a paired samples t-test. But you're always going to usually have at least 2 groups. Chapter 5 and 6, doing 1 sample, is mostly just to get your feet underneath you with what's a p-value and how to do a confidence interval so we can move on to more realistic situations. Okay.